All right, let's dive in. Today, we're going to crack open a really fundamental concept in any RF system: polarization. Seriously, this is something you're dealing with every single day, whether you're designing a satellite link or trying to figure out what's up with a mobile network.
Now, all this great info comes from a really solid source. This is part 10 of a big 20-part series, all based on an in-depth report about radio frequency propagation. It's put together by the folks at RFI Detectives, who are part of Virtualization Options LLC. And today, we're really going to zero in on a key chapter that gives us some powerful tools for the field.
So, why are we talking about this? What's the big deal? Well, this quote really nails it. Polarization isn't just some abstract theory. It's one of the most practical tools in our arsenal. It's a property that we as engineers can actually control and use to our advantage to build way better, more reliable systems. Okay, so let's get right to it. Before we can talk about controlling this property, we have to get on the same page about what it actually is. When you boil it all down, polarization is all about the orientation of the electric field as that radio wave is flying through space. Is it wiggling up and down vertically? Is it going side to side horizontally? Or is it actually rotating in a circle? That orientation is precisely what we can generate, select, and match up to make our RS links work beautifully. So let's open up that toolkit we're talking about. The first two major tools you're going to pull out are the linear polarizations. These are the absolute building blocks, the most common types you're going to run into out in the wild. And right away, you can see how these are two totally different tools for different jobs. You've got vertical polarization, which is just perfect for things like mobile and maritime communications, where you have simple whip antennas. It handles all those random orientations really well. Then you have horizontal, which is the absolute go-to for fixed systems. Think about TV broadcasting. Ever wonder why that's horizontal? Well, a big reason is that it helps cut down on interference from man-made electrical noise, which, fun fact, tends to be vertically polarized. See? It's a simple choice, but it has huge practical results. All right, we've covered the straight lines of linear polarization, but now things get really clever. Let's move into the rotation of circular polarization. This is where RF engineering gets super creative, especially when we're trying to solve some of the unique problems that come with communicating with things in space. Yeah, circular polarization is basically a specialist's tool. Take right-hand circular. When that signal bounces off a surface, something amazing happens. Its polarity flips to left-hand. So if your receiving antenna is only listening for right-hand signals, it just flat out rejects that reflected signal. It's an incredibly slick way to get rid of multipath interference, especially in satellite links. And it gets even better. By using both right-hand and left-hand signals, you can send two completely different streams of data on the very same frequency. You literally double your capacity. How cool is that? Okay, so we've laid out our whole toolkit. We have vertical, horizontal, right-hand, and left-hand circular. Now for the most important part, knowing when to use each one. And maybe more importantly, why you're choosing it. Look, in the end, your choice of polarization directly controls how well your system is going to work. This isn't just some detail you pick at random. It is a deliberate, conscious engineering choice you make to crank up your signal-to-noise ratio, to reject interference, to fight back against what the environment is doing to your signal, and to use our very crowded spectrum way more efficiently. So, mastering polarization is a huge step. But here's the kicker. As we're going to see in part 11 of this series, the real world often has other plans. You can send out a perfectly polarized signal, but reflections, refraction, and all sorts of other environmental factors can twist it and change it. And tackling that challenge is exactly what we're going to get into next time.